Good afternoon, everyone. Can you hear me well?
Hello, doctor. Yes.
Good. Okay, let's get started. So, do you have any questions before I start? Let me go to the assignment.
Yes,
where's
doctor.
the assignment?
Actually, I have a question about the assignment.
Yeah, good. Okay. So let me just find the assignment first. So I want to open the assignment and then take your questions. So here's the assignment. Assignment 2, right? This is it. Yeah. Okay, so question number, so do you want to ask now or when we get to the question? Because there are many questions here. Do you have...
I have a question in general. Not
yeah, please, yes, go ahead.
specific.
Yes, go ahead.
Doctor, we have things that we didn't talk about the last time, right? We have new things in the assignment.
Like what? Like what?
Like when we have this number about the matrix, I guess number 126 and 127. We didn't see this kind of questions before, and I didn't understand very well the difference between the arbitrary numbers and the non-zero numbers.
Okay, now we'll come to it and explain it, but I think I explained the basics, the very basics. Maybe we did not do exactly the same type of questions, but do not worry, now we are doing them. So now you will see some questions, right? And hopefully you'll be able to do them the next time. But this is not, I mean, it's not anything special. It's about just using the matrix, the augmented matrix, instead of the system itself. Okay. Now, if you have any specific questions about a concrete example, then you'll ask me later. Anybody else has a question about the homework in general? Okay. So let me open the book now. So this is 1 point.
Yeah. Yes, we have some problems in solving some of the numbers.
Yeah, okay. Yeah. Problems of what type? What do you mean by problems?
I found it difficult to find a way to solve some problems such as exercise 1.2.6 and 1.2.7.
Yeah. Okay. So this is what I think. Who asked now? I think Bakr asked now. Who asked this question before? Was it you, Bakr, or it was you, right? Oh, there are people here in the waiting room. Let me just admit them all. Yeah, okay. Yeah, so you don't have to worry. Now you will see now these questions, and they are not. I mean, they are simple questions. You just need to get used to them. And in fact, these questions are just to, if you like, inform you about the different types of systems, whether the system is consistent or inconsistent, and in what cases it is consistent, and in what cases it's inconsistent, and so on. Okay, we'll get to them. But let me first open the book so I can see the questions. So this is 1.2.1. How can I keep this and open the book now? I don't know. I think I need to go back to. I need to go back here to the book. This is the book. Okay, now I need to go back to the assignment. And see now what was this one. Okay 1.1 1.2.1 1.2.1 so this is somewhere here. Okay, yeah, 1.2.1. Okay, this is it. So the question is, find the point which lies on both lines, x plus 3y equal 1 and 4x minus y equal 3. So you could do it in different ways, of course. You could solve them just as a system of algebraic equations without any reference to the graphical representation. But you can also do it graphically using the lines, right? Each of these equations is a straight line in the plane, and the point of intersection is just a solution, right? So let's now just go to the solution. Here's a solution, okay? And here are the lines. So this is one line. So let me just go back to the question. So this is 4x minus y equal 3. This is the green line, okay? And the other one is x plus 3y equal 1, okay? This is the other line. And of course, the intersection is the point here in common, okay? And if you zoom in, now you can see that it is about 0.77. I mean, I did this in GeoGebra. So GeoGebra automatically would give you the coordinates of the intersection point. But of course, you could find it using elimination, for example, right? Or substitution, any method you know. But also you could do it graphically, right?
هلا دكتور.
Yes.
هلا انا طالعين معي بالفراكشن، انت عم تقول ان جيو جبرا دغري بحط لنا اياهم هيك، فانا طالع معي جواب فراكشنز حولته ديسمال بيطلع مش 0.08 بيطلع 0.07. بتفرق ولا لا؟ ما خاص انه حط تفرق.
And what else? 0.07 and then what?
لا اول وحده مزبوطه طلعت 0.77 وبعد في كثير ارقام، بس الثاني 1/13 طلعت 0.07.
Wait a bit, 1/13, let's do it. Calculator, this is calculator. 1/17, you said, right? 1/13.
No, 1/13, yes.
Yeah, 1/13, sorry, yeah. 1/13, all right. 0.077, right? So if you round up, it will be 0.08, right? This is what I did. I rounded up. Of course, now it's not good to write only 0.07. Now, of course, you could leave your answer. You could leave your answer as a fraction, and this is perfectly acceptable. So you don't have to round it up. But I took here the answer from GeoGebra, so that's why it's in decimals. But you could leave it as a fraction, and this is perfectly okay.
Okay.
The second question, which was 1.23. 1.2.3 so let me go to the book. Here's this. So do the 3 lines. So these are 3 lines here. have a common point of intersection? And if so, find the point, and if not, tell why they don't have such a common point of intersection. So now, of course, you could do it in many ways. You could find the point of intersection of these two lines, let's say, and check whether it lies on this line, right? Or let's say, take these two lines, find the intersection, and check that this point is also on this line, right? So you could do it in many different ways. But I did it again graphically. I did it graphically using GeoGebra, and GeoGebra shows you nicely that the three lines intersect at one point, right? And this point here happens to be, I think, a simple point where the coordinates, I mean, a grid point where the coordinates are 0.6 and 0.2. Okay, so it has x 0.6 and y 0.2. And you can check this easily by substituting in here. For example, if you substitute them in this equation here, right, it's obviously true, right? It makes it true. If you substitute them up here, then I think you will get the correct answer, right? And if you do it here, also you will get the correct answer. So it's obvious that this point here belongs to the three lines. So it's the intersection of the three lines. Okay. Any questions about 1.2.3?
Yes, I have a question on 1.2.3. هلا نحن ما قلنا انه فينا نعرف انه مثل prediction اذا ان number of equations كان اكبر من number of unknowns، يعني هي حتكون no solution.
Not always, but most probably there will be no solution, right? But it may be that there is a solution. Like here, for example, here there is a solution.
ما انا هذا اللي انصدمت فيه انه منا enough بس قول انا هيديك
لا ما هي it's not a rule. It's not a rule. Listen carefully. If you have more equations than unknowns, right? For example, if you have two unknowns and three equations, or let's say three unknowns and five equations, or four equations, right? Then what you should expect, listen carefully, what you should expect, right? That there will be no solution, right? But it may happen that there is a solution, like in this case here, there is a solution. Now, this shouldn't be a surprise. Wait a bit, this shouldn't be a surprise. In assignment 1, I believe we had a similar question, right? Where we had three equations. Let me go to assignment 1. Wait, somebody is waiting in the room. Let me just admit them. Just give me a moment, please. Somebody is waiting in the room, like, yes, okay. So now I'll admit them all to get in. Okay, yes, and let me show you now assignment 1, because in assignment 1, I believe that we had a similar question with three equations and two unknowns. So let me show it to you. Or didn't we? Oh no, not here, not here. But in the book, I think I covered one example in the book. Let me go to the book. The very beginning here. All right. I don't remember where. Let me just look for it. Yeah, this example. Look here. Look here. In the book, you see this example here. You have three lines, right? Which means that you have three equations and only two unknowns, x and y. And you see that the three lines intersect at a common point here. So this means that this point is a solution to the three equations. I mean, you think of it. What is more probable? Is it this case or this case? You see? What is more probable? So what is more expected? To have three lines not intersecting at a point, or to have three lines intersecting at a point? Now, certainly this case is more probable, right? If you are to draw just any three lines, right? Any three lines, you won't expect them to intersect at a common point, right? You would expect them to be like this, right? And that's why I'm saying that if you have three equations and only two unknowns, what you should expect, not be sure of, you can't be sure of it, but what you should expect, you should expect that there is no solution, right? But it may happen that there is a solution. Okay?
Yes, thank you, doctor.
Welcome. Okay, any other questions about 1.2.3? Okay, now we come to your question. Let me go back to the exercises. So this is the end of chapter. I think it's somewhere here. Yeah, here. Oh no, yeah, I skipped it. It's here somewhere. Okay, so 1.2.6. Consider the following augmented matrix, in which the star, or asterisk as we call it, denotes an arbitrary number. So it could be any number, including 0. Okay, and the square, this one, denotes a non-zero number. So it could be anything but not 0. Okay? Determine whether the given augmented matrix is consistent. And if consistent, is the solution unique? Okay. So now this is the question. Is it clear? So now you have here, you see any numbers you want, where you have the stars here, including zeros, right? But in the place of the squares here, you have only numbers with which are not zeros, right? Because the square, they said, is not 0. It's a non-zero number. Okay. And if you look carefully now, how many equations are there in the system? See, if we count the equations, it's
4.
4 equations, right? And how many unknowns do we have? How many unknowns do we have?
5.
5 unknowns, right? It's just every column is an unknown, right? So this is, for example, the x1, and then this is the x2, the x3, x4, and x5. And now, if you have less equations than unknowns, right? Then what should you expect? What should you expect?
Infinite solutions.
Infinite solutions, absolutely right. Infinitely many. It's like the case when you have, let's say, 2 planes, remember, which means 2 equations and 3 unknowns. 2 equations and 3 unknowns, which means 2 planes in the space. And we know that in this case, we expect an intersection between the 2 planes, which will be a line, right? And a line is an infinite set of solutions. There are infinitely many points on the line, right? Similarly, if you have one line in the plane, just x, let's say x plus y equals 3, right? So you have one equation and 2 unknowns. How many solutions? Infinitely many. All the points on the line are solutions, right? And this is the case here. We have 4 equations, and only 4 equations and 5 unknowns. Then we expect to get, in general, infinitely many solutions, right? But now it all depends on the value of this number here. You see this number here. If this number was 0, let's say this number here was 0. Do you see what I'm pointing at? Let me just try to. Oh, I can't. Let me run the annotation tool so I can annotate the screen. Just a minute. Okay. So I'm pointing at this entry here. This entry here. You see. You see, all the entries here are zeros, right? So this is the coefficient of x1 is 0, the coefficient of x2 is 0, the coefficient of x3 is 0, the coefficient of x4 is 0, right? And only the coefficient of x5 here, right, is some number, right? Now, if this number could be 0, let's say, right, then this equation would read 0 plus 0 plus 0 plus 0 plus 0 equals to some number here, right? And if this number was different than 0, then you would have an inconsistent system, because 0 can't be equal to something which is not 0, right? Some number which is not 0. This is impossible to have, right? But they said that this square, right, the square here itself, right, the square is not 0, right? It's a non-zero number. For example, it could be 1, it could be 2, it could be -3 or -7.8, whatever it is, right? But it's not 0. Then this means that this equation, right, the last equation, this equation is always solvable. You can always solve it, right? But whatever this entry here, including 0, it could be 0. For example, you could have, let's say, minus, suppose 2 times x5, right, equals 0, right? Then from here, what do you deduce? You deduce that x5 is equal to 0, right? Okay. Now it could be not 0 here, but nothing will change. It could be 1, this entry here. It could be 7. It could be whatever you want it to be, right? Then you will always be able to solve for x5, right? So this equation is always solvable. This equation is always solvable. Okay. Now suppose you have found a solution. Then what do you do with it? Now you have to remember back substitute, right? We have to substitute back in the other equations. So now you substitute this solution in here, right? In this entry here, in this equation here. And now look at this equation. How many unknowns will be in this equation? Do you see this equation here?
Sorry, Doctor, on which equation talking?
The one before the last. The one before the last. The third equation.
There will be 3 unknowns.
Yeah, but you have found one. You have found this one. You have found the x5, right? So you substitute it in here.
Unknowns.
There will be 2 unknowns, right? There will be 2 unknowns. In general, there will be 2 unknowns, right? Now, can you solve an equation into unknowns? What do you think?
Yes، مثل وقت نطلع نحن وحدة ويبقى عندنا مثلا equation بقلبها y و z وهيك عملنا هيك شيء قبل يعني.
Yeah, if you have one equation and 2 unknowns, then you expect infinitely many solutions, right? And you can use, for example, the parametric representation. You can call one of the solutions, let's say t, and then you will find the other one in terms of t, the other unknown in terms of t. So this equation is certainly solvable. Okay, I mean the third equation. And now once you have once you have found the solutions, now you substitute them back in this equation, in the second equation. Now, will you be able to solve this equation? Yeah, certainly, because you see, this coefficient is not 0, right? So you have found now, you have found the x5, the x3, and the x4, and now you are looking for x2. So whatever the values of x3 and x4 are and x5, you will always be able to solve for x2, because this coefficient is not 0. And now once you have the x2, you substitute them all in the first equation, and you solve for the x1. Right, whatever it is, in terms of t, of course, everything will be in terms of t. And then, so what do you say about this system? Is it consistent or not? Certainly it is consistent. Now, is the solution unique? Certainly not, because you have, as we said at the beginning, we have 4 equations and only and 4 unknowns, right? So we expect to have infinitely many solutions. You see, I mean, everything, of course, will depend on the values of these stars here. So you can't be sure whether there will be, but in general, okay, you expect it to have infinitely many solutions. You expect it to have infinitely many solutions. Okay, so this is my answer, which I'm giving you here. This answer here is consistent, which means it admits at least one solution, and it admits, we say, a 1-parameter solution set, which depends, usually we call it T, or you can call it whatever you want, U, V, whatever, okay, since there are 4 equations and 5 unknowns. So when I say a 1-parameter solution, I mean that there is one number in the solution which is undetermined. Okay, so it can take any value, any real value you want. Okay, any questions about this one, about number 1.2.6? Again, people are waiting in the room. I'm not getting any notifications that people are waiting in the room for some reason. I don't know why. So,
Doctor?
hello?
سوري
Hello, can you
دكتور
hear
راحت
me?
الكهرباء بس.
Yeah, it seems everywhere because I also got disconnected. So I asked, do you have any questions about number 1.2.6?
Doctor?
Yes.
Actually, Doctor, I don't understand very well.
Yeah, okay. So let me take each one separately. Somebody had a question before, Becker.
أنا دكتور.
Yes, please.
يعني دكتور فينا نكتب لهم بس إنه since it is 4 equation with 5 unknowns we expect to have infinite solution.
Yes, in this case, yes, but in general, no. Like, for example, imagine you had here, so let me take you back here. Imagine here, you had, instead of this, where was the question? Yeah, this one. Instead of this square here, let me just again show you. So let me say, instead of this square here, right, you had a star, let's say, right? Let's say you had a star here, which means that this number could be 0, right? Because you see, the star means it denotes an arbitrary number. Arbitrary means any number, okay, including 0. It can be 0, right? So if this number could be 0, right, then the last row, this row here, right, could in principle be 0, 0, 0, 0, right? And here, let's say, instead of this star, you could have 1, let's say, right? Then how could you make it? How could you make it true? How could you have 0 equal 1? This is impossible, right? It's impossible to be true, right? Because the left-hand side would be 0 everywhere, right? You see? And the right-hand side would be 1. Now, this is impossible. So in that case, if you had here a star instead of this square, right, then the system could in principle be inconsistent. So in that case, there would be no solution. What?
We consider the square as a star?
No, yeah, back here. The square is any number which is non-zero, okay? So any non-zero number. So this square can't be 0 here. This square also can't be 0. This one can't be 0, and this one can't be 0. So the square can be any number but not 0. If you are saying anything, I can't hear you. So Fatima, do you still have a question?
Doctor, I have, please. I understand, but please, if you إذا عندك السوليوشن تقدر تبعت لنا إياهم لحتى نقدر نعرف نكتب بالصيغة مظبوطة.
Yeah, okay. Yeah, of course I will share the solutions with you. I'm not sure that did I share the solution to the previous assignment with you. I'm not sure, but I will make sure to upload this solution today after our class. Okay, I will upload this solution,
Okay,
the one I'm using now here. I will upload it later to Teams. Yes, we can download it from Teams.
Thank you, Doctor.
Welcome. Fatima, do you still, Fatima Faris, do you still have a question on this one, on 1.2.6?
I asked إنه هذا الشيء كافي بس نكتب هيك بهيدا.
Oh yeah, of course, yes, because you see, you don't know these numbers, so it depends I mean, it all depends on these numbers, okay? But as long as this number is not 0, this entry is not 0, right? This one is not 0, then you can be sure that the system is solvable. You can solve it, okay? And because of this, it's consistent. Bakir.
Yes, doctor.
Yes. Do you have a question?
No. My question was, you were saying that the square is a non-zero number and the star is an arbitrary number. So you said that we cannot have, of course, we cannot have 0 equal to 1. This was my question.
Yeah.
I understand.
Okay. So the next question is, I think, 1.2.7, which is very similar to this one, right? 1.2.1.7. This so it's somewhere here. This one here. Yeah. Consider the following augmented matrix in which star denotes again an arbitrary number and the square denotes a non-zero number. And determine again the same question whether this is consistent, and if it is consistent, whether the solution is unique. Okay, and you see that it looks almost the same as this one, except now we have the same number of equations, right? As the number of unknowns. We have 3 equations in 3 unknowns, right? And now let's see, could we always solve the system? Could we always solve it, right? Again, since this number is not 0, right? Now, you may wonder, why am I looking at the last equation? Why am I looking here, not here? Okay, because you see this equation has 2 zeros in it, right? These 2 zeros, and only one entry, this entry here is not 0, right? So this means that the last equation is saying 0x, if I want to write it in terms of